Did go get sick? He signed up.
That's weaker shop.
Okay, so I got some good, I think pretty good optimization problems. Get into more like engineering type applications maybe. a little bit like this. Okay, so minimum surface area. So what about this one? If we've got, and this is where, with these problems, as you've already recognized, it's not so much the calculus as it is being able to set it up, right? Being able to turn the situation into a math model that's going to work. So a solid is formed by adjoining two hemispheres to the ends of a right circular cylinder. What's that going to look like?
You got a cylinder, and then you've got like a pill.
So like a pill, exactly. It's going to look like a pill. Okay, so it's going to look like
Maybe we're designing a pill.
kind of like that, right? Okay, does that make sense? And so this would be a model of, like a high pressure vessel or something, right? Like a propane tank or something along those lines, okay? So we want to, if we know that the total volume needs to be, so this probably is a pill. I mean, this is, or it's not a pill, but it's pretty small, 14 cubic centimeters. We want to find the radius of the cylinder that produces the minimum surface area, okay? So if we wanted to break this up into like dimensions, the radius of the cylinder is also going to be the radius of the hemispherical caps, and then the only other dimension we would have would be maybe something like the height of the lateral part of the cylinder, right? But it doesn't even ask about that. It just wants the radius of the cylinder that's going to fit that constraint. It's going to minimize surface area, right? Okay, make sense?
So is that just, then it's just basically asking for the smallest circle or sphere.
It's going to ask for the smallest shape that's going to contain 14 cubic centimeters, right, of volume. The smallest surface area that's going to contain that. Do you have any predictions?
Why don't you just have a circle? Like what, if there's no...
You mean a sphere?
Yeah.
It might be that.
Okay.
That's a possibility. It might be that. Yeah. But we're assuming that it's going to be a capsule like this, and it might sort of devolve into a situation where the right. Oh, sorry about that. Question brought those to you.
I forgot to get.
Where the lateral area of that cylinder might just go away completely. It's possible, right? Okay, so what are we going to do with this then? Here's our problem. So we got a picture. Let's run through the calculus. So what's the first thing we want to do?
Well, we're going to be solving for the surface area.
Okay, so
let's write that formula out first.
okay, good. So there's our primary equation, surface area. All right, so surface area is going to equal, in terms of, like, if we call the variables, how about if we call the variables, just to make things simple, well,
R and A.
okay, R and A. That's fine, they're there, R and A. We can do that. Okay. What do we get?
So we're going to, let's see.
How would you think about that
A.
surface area?
A tau R.
Tau R. He likes his taus. Okay, in terms of pies, how about?
What is a tau? 2 pi.
So what's,
1 tau is 2 pi.
yeah.
Thus it's superior. So 2a pi r.
It's the circumference of the unit circle.
That
There are proponents of tau that think we should do away with pi. Milton's quickly falling into that camp.
Yeah.
Okay.
Plus, so what's the surface area?
So the end caps combined, would everybody agree that end caps combined, you can kind of reconfigure this in your mind. The end caps just make a sphere.
Yeah.
So we got surface area of a sphere,
So pi r
so
squared.
4 pi r squared,
Or
good,
2 tau r squared.
or 2 tau r squared, okay, plus, plus all we want is the barrel, right, the lateral surface area of the cylinder. So how do you think about that?
It's circumference times the height.
It is circumference times the height, and so you could think about it, if I took that, like the toilet paper roll, what this is essentially. If I took that and I cut it and I unroll it, it's going to become a rectangle where the length is just the circumference, right? And then the height is A. Okay, makes sense? So 2 pi r times A. Okay, what's the obvious problem with that? Two variables, R and A, right? So we need to come up with our constraint, and our constraint has to be related to, our secondary equation has to be related to the one constraint we have, which is on volume. Okay, so what is the volume of this capsule?
Volume was 14, and volume will equal volume of the sphere plus volume of the cylinder.
Okay, so 4/3 pi r cubed would be the volume of the sphere we get from the two hemispheres combined, plus volume of the right circular cylinder would just be the cross-sectional area times the height, right? So pi r squared A. And that whole thing, we're told, equals 14. Okay, make sense? So then what's our strategy here? Good, we definitely want to connect the A's, don't we? Because there's one in each equation, okay? I've got two R's, different powers of R in each equation, that's a mess, right? So we're just gonna solve for A and then substitute. So what do we get if we solve for A here?
14 minus 4/3 pi r cubed divided by pi r squared.
So we're gonna subtract that term away, good, 4/3 pi r cubed divided by pi r squared. Okay, so we can simplify that a little bit, can't we? So the first term is fine. What about this other term? We're gonna get minus, so on the other term, the pi's would cancel. I would get an r squared canceling, right? And so on the top, I could break it into a fraction. On the top, I'm gonna get a 4, on the bottom, I'm gonna get a 3. And all that's left on the top, the pi's cancel, and r squared cancels, so we get an r on top. Everybody agree? That's my substitution equation. Okay. All right, so there's A. Now we can substitute back in. If we plug that back in right here, what are we going to get then? So we get surface area equals 4 pi r squared plus 2 pi r times that whole thing. Okay, good. So S equals 4 pi r squared. So if we distribute then, what are we going to get?
Are you recording?
I am recorded. Thank you for asking.
Katie just texted to make sure you are.
Oh, okay.
Yeah.
Yeah.
You're going to get 28 over r minus 8 pi cubed, 8 pi r cubed divided by
All right, one term at a time. So first term, pi's cancel. I'm going to have an r cancel with one of the r's on the bottom.
Yeah.
And so I'm left with 28 on the top and just an r on the bottom. Good.
Yes.
So plus 28 over r. Second term, we're going to get an r squared. 2 pi times 8 is 8 pi over 3. So I'm going to get a plus 8/3 pi r squared. Now these are like terms, aren't they?
Isn't it minus?
Say it again.
Isn't it minus?
Oh, minus. Whoops, you're right. Okay, so those are like terms. We could combine those. And so this is going to end up looking all right, isn't it? This is S of a single variable r. And let's see, 4 pi r squared minus 8/3 pi r squared. Well, 4 is 12/3. 12/3 minus 8/3 is just 4/3. Okay, so we get a 4/3 pi r squared plus 28 over r. There's our, so all that work essentially gets us to where now we can just shift into calculus mode and do a table, right? But we still need the domain, right? What would the domain be for this? What's the minimum value that, the lower limit for r?
It can't be 0.
Can't be zero, but we could go down approaching zero, right?
Yeah.
Okay, now what about the upper limit? Think about what's gonna happen here. If the volume is fixed, Ryan, what's gonna happen to, the variables always are gonna compete, aren't they, in these situations, right? Or it wouldn't make sense. I mean, if one variable gets bigger as the other variable gets bigger, then it's a runaway train and the constraint doesn't do anything, right? So the constraint is always gonna pit the variables that are inversely related. As R gets bigger, A gets smaller, because the volume is fixed. What's the smallest value that A could have?
Zero.
Could be zero, right? If the barrel disappears completely and it just devolves into a sphere, right? So if A is zero, where would we go to figure out what R is gonna be if A is zero?
The great train is
Where? Volume, okay, we could, but we've already kind of done some work here, haven't we? Right, where we've already done some work relating A to the other variables. Well, if A goes to zero, that becomes a pretty easy equation to solve, doesn't it? Right? So, let's do this. So, when A equals zero, we end up with 14 over pi r squared equals 4/3 r, right? Everybody agree? I can solve that. I get a proportion there, right, a ratio equation, so I'll just cross multiply. And so I get 4 pi r cubed, I'll put that r in the top, in the numerator, equals 42. So r cubed equals 42 over 4 pi, which is 21 over 2 pi. And so r equals the cube root of 21 over 2 pi when a equals 0. That's our upper limit. That's a pretty inconvenient number, so let's just approximate that. What is that roughly? Anybody have a calculator handy? I can just use Desmos if not. So r is roughly equal to, okay, good. Cube root of 21 over 2 pi. About 3 point, are you sure that's the, but we wanted the cube root of that though? That doesn't seem right. 21 over, it's about 3-ish, so seems like it's gotta be 1 point.
Does that have to be in gradient?
1.5. Say it again?
Will have to be in gradient.
No, it doesn't make any difference. 1.5, about. Okay, so our upper limit's about 1.5 for R. So we'll go back over here, and so we're going, that's going to be our domain for R. Okay, whatever units, I think we're centimeters, right? And now this just becomes a calculus problem. Right now we would just find the first and second derivatives. If second derivative would be easy, so we should do it, right? And then we'll just make our table and find what the minimum for surface area is, right? So what's our first derivative going to be? First term, if I differentiate with respect to R? 8/3. Good, bring the 2 out, so I get 4/3 times 2 is 8/3 pi r. Derivative of 28, now how do I do this one again? Good, so it'd be 28r to the minus 1. Derivative of 28r to the minus 1 is, good, minus 28r to the minus 2. Okay, so there's my first derivative. Okay, the second derivative, can you tell me right now, just kind of, you're building some intuition here. What's going to be, our domain is all positive values of r. What can you tell me right now about the behavior of the second derivative? It's always going to be positive, isn't it? Right? Because I'm going to get two positive terms, right? And so I'm always going to get back a positive result, which means it's always going to be concave. If it's positive, concave up. So we are getting a minimum there somewhere, right? Okay? So second derivative is going to give us 8/3 pi. And then here I've got the derivative. Really what I'm doing is I'm taking the derivative with respect to r of negative 28 r to the minus 2, which would be positive 56 r to the negative 3. Right? So any value of r I plug in there, I'm getting positive results. Right? So this is greater than 0 on our domain. Okay? But we do need to know, we got to go back to our first derivative and see if we have some first derivative critical numbers. All right, so where would, we got to get derivatives or critical numbers of the first derivative. Well, one of them would be 0, but 0 is not in our domain, so we don't care. Right? We know that's where to be undefined. So now we've just got to set the first derivative equal to 0. Okay, so then, I gotta go to the next page. I have to squat down, right? Yeah, it's not comfortable for an old fart like me. I'm gonna. And so if we carve out a little space here. So there's our first derivative, right? So we know s prime equals 0 when what? If I set that equal to 0, we'll just add that term to the other side, so when the terms are equal, right? So s prime is 0 when 8/3 pi r, and let's write these as fractions. So 8 pi r over 3 equals 28 over r squared. Right? What could I do? I guess I could divide each by 4? No. By 4. Right? I could make this, if I divide each side by 4, I could make that a 2 and that a 7. Makes it a little easier. Yeah. Right? And if I cross multiply, I'm going to get 2 pi r cubed equals 21. So if I solve for, what's going on here? Right? Kirk was right, wasn't he? If I solve this thing, we're going to get, if I solve for r, I get r cubed equals 21 over 2 pi. So r equals the cube root of 21 over 2 pi. Well, that's our 1.5, isn't it? That's the endpoint. Okay? So when we make our table, so our domain was from 0 up to, actually, there's a little bit, one small mistake on that domain, because I really shouldn't have put a rounded endpoint on that, should I? Right, because how did we get that, right? We said we got that because...
So it's fine.
Well, okay, but we got that by saying what happens when A is actually equal to 0, which it can equal, right? So when A is 0, R really does equal this. So that really should be included in our domain. So I really should go back here and fix that. When I say fix it, I mean that should become square bracket, right? Because we do include that endpoint. Right? So then in our table, and I'm not gonna, I'm just gonna approximate it as 1.5. So I don't wanna write down the whole, we make our table. We'll just say our upper limit is approximately 1.5, and that is where we got our 0 for the first derivative. Our second derivative we know is positive everywhere, right? And so we know it's an endpoint, but it's gotta be, that has to be the lowest value then, doesn't it? Right? Okay. So we know that's gotta be a minimum, that endpoint does. That's it. So it makes sense, it stands to reason. This sort of informs our previous discussion. We talked about why animals are basically spherical in shape. Well, this is just another chapter in that story, isn't it? We know that the most efficient way of encapsulating volume is to put it into a sphere, and so we would collapse that into a sphere if we want to get the most volume in the least surface area, right? Okay? So on the assignment, so you guys saw that there's, so I added a paper and pencil assignment for Sunday. Okay, here's 2 problems, and I want to see you actually write these on. Instead of just getting the answers this time, I want to see you write them on paper, but you're going to grade yourselves. I've got the solutions up already, but I want you to try to do these without the solutions. Right? Do your best, and I'll just get credit for doing the work. I mean, this is like a college level class. So. Well, no, we didn't. We didn't, because this is the problem you're going to do. A better problem. Okay, the problem you're going to do is a more realistic problem. Now we're actually building an industrial tank, same shape, right? So it's going to be that same pill shape, but this time it's going to be a big industrial tank where the capacity is 4,000 cubic feet. Okay, this time though, we're trying to build this in such a way that we're going to minimize the cost. And here's the key part of this. The spherical ends, the hemispherical ends, cost twice as much per square foot of surface area as the sides, which is realistic. I mean, if you're building a tank like that, what's going to be easier to do? You know, build the barrel. That's easy, right? You just take a piece of sheet metal and you fold it up into. I mean, that's probably an easy thing to do. But to create those hemispherical end caps, that's harder to do. That's going to require more engineering. It's going to be hard. It's going to be more labor intensive. That's going to cost more. Right. So this is a realistic kind of a problem. This is the kind of thing that an engineer would run into. If you're like a civil engineer, this is exactly the kind of calculus you're going to do when you're building some kind of a silo, or you're building some kind of a high pressure vessel, and that's pretty frequent, right? Okay, so then how do we set this one up? We've done a lot of the math, and I'll help you guys set it up, and you're going to go from there, right? So we did a lot of the math right here. Here was a really important equation for us, right? S equals 4 pi r squared plus 2 pi ra. But we've got to modify that a little bit, because now it's not just a simple surface area. It's what we in math what we call a weighted surface area, right? There's a weighting to this because we're actually paying money to have this thing built, right? And we know that the end caps cost twice as much. So what would I do to that surface area equation to change it into a cost equation?
Multiply the spherical surface area by 2.
Okay, so now we got to be a little bit careful. We got to be a little bit careful with this. You're on the right track. You're absolutely on the right track. But there's one additional little part of this that we got to be careful of. So we know C equals. There's the 2 hemispherical end caps, right? Should be 4 pi r squared. Okay, and then we ended up with 2 pi r a is the area of the sides, right, the lateral sides. But how do we introduce this stuff? The hemispherical ends cost twice as much per square foot as the sides do. Do I just want to attach a 2 and a 1 there? What's wrong with that?
It'd be like 2x.
It'd be like 2x. Okay, it's got to be, because we don't know. If I put a 2 out there, that's actually making the implicit assumption that, okay, the cost per square foot is 2 something dollars or thousands, whatever it is, and this is 1. It might not be. It might be that this is $7 per square foot and that's 14, right? We don't know what the specific cost per unit area is, all we know is that this one is twice as much as that one. So we don't want to use, well, we could use x, but usually we would avoid using x because x is almost always a variable. What do you think we ought to probably do here? Instead of x, maybe k. K is exactly what we normally probably do. We'll pick a symbol that usually corresponds to a constant, like k, and we'll plug that in. So the end caps, those are going to be maybe 2k is going to be the cost per square foot, and the lateral surface area of the sides, that'd be more like k dollars per square foot, right? So we're going to multiply the more expensive parts by 2k and the least expensive part by k, where k equals cost per square foot of the lateral area, we'll call it, right? The area of the barrel. You know, that changes things, doesn't it? Do we expect that this is going to end up being just a sphere now? It's not going to be, right? This time it's not going to be because the end caps cost too much to do that. It's going to be somewhere in the middle. There's going to be some ideal shape that's going to minimize cost, and it's going to be a little bit different when we introduce these two factors. Now, one thing you can do, looking ahead, we can do the same. We can just borrow. We can borrow this, right? Because this part, well, I guess it can't. It's not 14, so it can't quite be that.
We can take it 2 out for a second.
We know that the volume has to be 4,000 cubic feet. So that's our primary equation. We got two variables. Our secondary equation now would just be 4/3 pi r cubed plus pi r squared a equals 4,000 instead of 14, right? So we're still going to go through the same process we did last time, only we got a 4,000 there instead of a 14, right? And we're going to have to substitute for a. When we're all done with that, we're going to get cost as a function of r only. Okay. Now, what about this k? Do we need to drag that k through? No, we could even factor the k out in front of everything if we wanted, right? The k is not going to be significant. Well, maybe, but remember, when we substitute for a, things are going to get a little wonky. Some of the pi's are going to get canceled and some aren't, right? But we know that we've got whatever we're going to multiply by. I'm going to have a k times a bunch of stuff and a 2k times a term. I could just factor the k's out in front and just leave them there the whole time. They're not going to impact my solution in any way at all, right? The only reason we attach that k to it is just because we don't know specifically what the costs are. The nice thing about it is we could do a little research when we're all done with the problem and figure out what they are and plug them in later, and everything will still work. That's what we call a parameter in math. Okay? So I'll let you guys mess with that. And I've got detailed solutions I drew up last night that are already on Moodle, so that you can look at them, but try to avoid that as long as you can. Try to do what you can first.
That's the next assignment or 2 assignments?
That's the one for, that's number 5. It's the paper and pencil. Okay.
You know that when that's due?
I think it was Sunday. Yeah, pretty sure. And honestly, a lot of the work probably is pretty much done on this, and I'll put the notes up today, right? So we did a lot of the same kind of thing you're going to do. You can just sort of follow along this process. Okay? Okay, here's another, shift gears a little bit. This is another category of problem that you see a lot in math. And these probably seem kind of contrived, but this is actually a really good type of problem to do. It feeds into things you'll do for years and years and years in math. Okay, where you've got some envelope that's containing an object and you want to maximize, say, volume contained within this geometric envelope. In this case, we want to find the largest right circular cone. So there's a prototypical right circular cone. That's what we mean. Okay? That can be inscribed in a sphere of radius 13. So what's the biggest cone that we can fit into a sphere of radius 13? That's a pretty cool problem to be able to solve. You can't do that geometrically. I mean, you have to do this with calculus. There's no way around it. Okay. So the picture you would draw here's what I kind of want to talk to you guys about a little bit, is how do we turn this into a workable calculus situation? Because it's not like this is an obscenely hard problem, but it's really hard to get this thing built where you can assign some variables that are going to make sense, right? This is the part that's a little bit tricky. So what we want to do with this is, let's draw this in the simplest possible way, right? Well, three-dimensional drawings are totally unnecessary here. We could just cut right through the center of this thing in cross-section, and this is what the cross-section of the cone is going to look like. It's going to be a right triangle, or a isosceles triangle, right? You see that? And then the cross-section of the sphere is obviously a circle. So we know that the height, we define the volume of the cone in terms of its height and its radius. So here's where they would show up in our cross-section, right? The height of the cone is just that distance. Agreed? And the radius of the cone is right there. Okay? Now, the constraint is that the radius of the encapsulating sphere is 13. Where would that fit into this drawing?
Radius, not C.
Okay, but where would that's just like we did with related rates. When we're drawing a picture where we've got variables and constants in there, we always want to write the constants as a number so we don't confuse it with the variable, right? Where would I put the 13 in my drawing? No, it's not the radius of the cone. Don't confuse the two. It's the radius of the sphere that's containing all this that's 13. So it's going to be, everybody see, it's going to be the red lines. Everybody get that? Okay. So now we've got a choice, right? Do we want to, somehow the problem we have with this is that I've got two variables that I need to somehow connect those, right? Well, where does the secondary equation come from? It's got to be the constraint. If there's no constraint, I say, let's just make this thing infinitely big and we're done. That's pretty easy, right? But there is a constraint. The radius of the sphere is 13, okay? So now, we know what's going to happen. So I'm going to lose my 13s when I move this thing. Yeah. So let me redraw that. This is kind of an important step though, right here. So we can either write this in terms of H and R, or if we wanted to, we could say, okay, well, we could define this in terms of maybe X and Y, where X and Y end up being convenient variables for connecting to the 13, because then they end up being the sides of a right triangle. See what I'm saying?
Yeah.
There's no one way that's better than the other. I would tend to do it this way. Okay. Either way, you're going to have to set up an equation of constraint, but it's just easier to set up here than it was here, right? So if we're going to write, now let's take this picture, for example. I think I had enough. No, I didn't, of course. All right, well. Copy this to the next page. Okay. So how are we going to write this volume now in terms of the variables X and Y? So volume is going to equal pi thirds. What's my radius in terms of this picture? Radius of the cone, X. And what's the height?
Y plus 13.
Y plus 13, right? Okay. So we still get two variables there. So we still have to have an equation of constraint. But now we know, okay, the equation of constraint comes from the 13, right? So based on this little triangle right here, that's the triangle that we want. This guy right here. What's the relationship between X and Y?
X squared plus Y squared equals X squared.
There you go, right? So we get the constraint, X squared plus Y squared equals 169. Okay, now slow down here. Don't jump into any rash, don't be hasty with your decision, but what variable do we want to substitute for? X squared, for sure, right? Because if I solve for y, I gotta introduce a square root there. I don't like them. The calculus gets hard with square roots, doesn't it? So instead, we can see we got a connection right here. Right? All we gotta do is isolate that x squared and make the substitution. That's easy to do. What is x squared in terms of the rest of the stuff? Well, 169 minus y squared, right? And what do they want from this? All they want is volume, right? If we look at what's actually being asked here, they don't even care about the dimensions. So we're not even gonna have to go back and ever do any square roots, right? We don't ever even have to go back and find out what x is. We just want the biggest volume, okay? So if we make that substitution, then we end up with v equals pi thirds times x squared, which is just 169 minus y squared times y plus 13. Well, that's v of y, isn't it? Right? And that's a pretty easy, and you can look ahead and say that's going to be pretty easy, right? When I expand this out, that's just going to be a polynomial. I've got this pi thirds out front, big deal, it's just a constant, right? It's not going to impact the derivatives at all. So that's going to be a really easy one to do. We just need our domain. So what's the smallest that y would reasonably be in this? 0. There'd be no reason for y to ever be, like we would never, if we're trying to maximize the volume of that interior cone, how dumb would this be for us to, for example, say, okay, well, we're going to have the cone go from there to there. That'd be pretty dumb, right? Because for the same radius, we could have a bigger cone, right? So the smallest y would ever be would be 0. And it could be 0. Probably not a wise choice, but it could be. What's the biggest y could be? Or what could it approach? 13, right. But if it were 13, then what's going to happen? Well, if it were 13, we're going to end up getting 0 for our volume, right? So there's no mathematical reason that we couldn't do it, but it's just not a good choice. Somewhere in there, we're going to get our maximum for volume, right? And all we'd have to do, I won't even finish this one, right? You guys, this is no big deal. All we'd have to do is just multiply that out so we don't have to do product rule. We're going to end up getting v of y equals pi thirds times some polynomial. Differentiate twice, which is easy to do for a polynomial, right? Find our critical numbers and check them, okay? All right. How much time we got? 2 minutes?
Yeah.
Oh, man. Okay. I got to fit this in at some point, because I'm not even gonna have you guys. I just want to walk you through a proof, kind of. So you guys remember what Snell's law is?
Yes.
Yep.
What does Snell's law tell you about optics?
Tells you the angle, the light is, yeah, incidence of refraction.
Okay.
It's
I can write the formula.
Does it look something? Remember it looking something like that?
Yes.
Yeah.
Oh, what do you know? Okay. So it looks something like the sine of the angle of incidence divided by the speed of light in that medium, right? And you might have phrased it in terms of an index of refraction. You're probably right. But what does an index of refraction really mean? It's all that's doing is predicting the speed of light in that substance, right?
Yes.
So it looks an awful lot like that, doesn't it? Okay. So this is the part that's super cool. You can, and this is really kind of, I remember doing this in college, and it's really kind of satisfying to be able to do this because it's all geometric. You can derive all of the important optic equations, even the ones that transcend geometric optics, like the really big time ones you get when you get into calculus-based physics. They can all be derived using a principle called Huygens principle, which just says that light will always prefer to take the path of least transit time. And if you do that, you can easily prove or evolve to get all of these optical relationships from that one simple, super simple relationship, right? And there's some really profound we gotta have a long talk about this, because there's some really profound consequences for it. It has to do with, it even impacts the idea of what would our relationship be to a parallel universe? I mean, there's some really interesting, if you kind of stretch your thinking on this, and come to some fascinating endpoints from the discussion. But I want to just show you guys, I want to take a day and just show you how we can take a completely unrelated problem, like a guy driving a boat up to a beach, and then trying to minimize his time going from some point offshore to some point onshore, and show you that it comes up being Snell's law, right? And there's your proof. All we did was we minimized transit time, right? To me, that's just super cool. But we'll do that some other time.